Hi students, welcome back to my lecture. In my last lecture, we have discussed about the mesh number and standard screen. In this lecture, we talk about the screen analysis. In the screen analysis, the objective of the screen analysis is to find out particles of different diameters and different amounts. Let us go ahead how to do the screen analysis. Example, I have some material with me for which I have to find out different diameter particles in that amount and what are its different amounts. What I do is I take all the material, I put it on the top screen and I subject the screen to the vibration and rotation motions and tapping motions. During so, the bigger particles will be remain in top screen and smaller particles will come down, right, because of this small in nature. So different particles of different sizes will be present on different screen after the sieving motion, screening action. So the one with the bigger size will be there at the top and the one with the smallest size will be there at the pan, and the intermediate sizes will be distributed among the each screens. Our objective is to find out what is the particle size. Okay, let us go for the first agenda. Example, this is the screens which I have in my lab is for mesh number 4, 6, 10, 20, 30, 60, 100 screen and pan. For example, after the screening analysis, you have to find out the particles on mesh number 6, size of the particles on the mesh number 6. How we can define the size? The particles on the 6 mesh will have the size between these two screen diameters because it has passed through 4 screen, it has retained on the screen number mesh number 6. Mesh number 4, it has passed through and is retained on the mesh number 6. So what is the particle diameter on my 6 now? The diameter of the mesh number 4 plus diameter of the mesh number 6 divided by 2. That is the average particle diameter that is there on the screen mesh number 6. Then what is the diameter on the mesh number 10? Because the particles has passed through 6 and retained on the 10. That means the average particle diameter that is there on the screen number 10 is the average of 6 and 10. That means diameter of this mesh 6 plus diameter of the mesh 10 divided by 2. So that is the particle diameter that is there on the mesh number 6. Similarly, we have to calculate, example, this is 100. What is the particle on the 100? The one which has passed through 60 and retained on the 100. That means the particle diameter on the mesh number 100 is the average between 60 and 100. That means diameter of the 60 screen plus diameter of the 100 screen divided by 2. That's the arithmetic average we are calculating. Then what is the pan? The particles which is there on the pan, there is no such a defined diameter. So in the lab, what we do is, there is pan, it's just a container, it don't have any diameter. Now the diameter is 0. So the particles which are there on the pan is the diameter of the 100, pan diameter is 0 divided by 2. That is the particle diameter that is resided on the screen number, on the pan. So this is how we can define the particle diameters which is there on different mesh screens. Okay, this is very important aspect because from this, if you talk about the standard screens, because we don't have the Taylor standard screens, because if you talk about the Taylor standard screens, there is certain ratio to be maintained. Example, I don't have the Taylor standard screens, but for example, screen number 4, mesh number 4 and mesh number 10. The diameter of the mesh number 4 and to the diameter of the mesh number will be 1.4. That means whichever the screens, all screens should maintain some ratio. The ratio of the bigger screen to the smaller screen is 1.41, that means root 2. If it is maintained on each and every mesh, entire screens, then it is comes under the Taylor standard screens. Example, only just for example, diameter number mesh number 4 to the diameter of the mesh number 10, if I take this ratio, it should be 1.2. Similarly, mesh number 10 diameter divided by mesh number 20 diameter, it should be also 1.41. So for that, every two screens, if I take the ratio, it has to be 1.41 root 2. Okay. If I have such a kind of mesh with me, then that is called the Taylor standard screens. Presently, let us, whatever the screens we have, I will do some example on the board to find out different aspects. What are the, mass fraction retained on the every screens, and what is the cumulative fractions? Let us do this analysis. Before I do that, let me define a few terms. This is called increment because whichever the diameter of the particle here, we call it a separate name. In this increment, what is this diameter of the particle? In this increment, what is the diameter of the particle? In this increment, what is the diameter of this particle? Because once you go to the board, you find this term in the increment. In increment means from this to this increment, what is the particle diameter? In this increment, what is the particle diameter? Like that, we have defined particle diameters in the each and every increment of whichever this mesh I have here. Okay, let us go to the board. Hi students, let us continue the class on screen analysis. With the screens which we have, based on that, we have measured different diameters of the particles. For example, whatever I have been written on the board, I have formulated a table. In the table starts with the mesh number, right? I have mesh number 4, 6, 10, 20, 30, 60, 100 pan. The diameters are defined for these meshes. That means the mesh number 4 has opening diameter of 0.699. Mesh number 6 has got opening diameter 0.327 mm. Similarly, for pan, as that is container to collect, there is no opening diameter as such for pan. We are taking it as a 0. For average particle diameter in the increment, as I told you, every increment, that means if you compare any two screens, I have to define the particle size for those screen. Example, if you leave the top screen a bit for some time, let us take example of screen number 6. What is the particles on this diameter of the particles on screen number 6? The particles on the screen number 6 has come from the screen number 4. That means it has passed through screen number 4 and stopped on the screen number 6. What is the particle diameter on the screen number 6 then? Average of 4 plus 6 by 2. Okay, that means the particle diameter 4.013. Okay, it has come from 4.699 plus 3.327 by 2. Then imagine the particles which is there on the screen number 10. What is its diameter? That means it has passed through screen number 6 and stopped on screen number 10. Then the particle diameter on the screen number 10 is average of 6 plus 10 by 2. Similarly, you can define the particle diameters of all the particles on each and every screen. What is the pan? The particles on the pan, what is its diameter? Because as such pan diameter is 0. Okay. The one there on the pan, it has come from the screen number 100. That means screen number 100 plus pan 0 by 2. That means 0.073, the particle diameter of size 0.073 has come 0.147 plus 0 by 2. That is what the particles diameter on the pan. This is how we can define what is the particle diameters on each and every screen. For the top screen, I have written 25, right? Because top screen is the number 4. How I can define the particles on the screen number 4? Because there is no screen above it, because if there would have been a screen of number 3 on the screen number 4, the particle should pass from the screen number 3 and should stop on the screen number 4. The particle diameter on the screen number 4 is 3 plus 4 by 2, something like that, but there is no such a screen over the 4. What you people supposed to do is take out different particles, measure its diameter manually, take circumference, take a thread, make it circumference, and it's averaging way. Take out average of all those particles on the screen number 4 and tell the average. Because we have measured, we have taken 3 to 4 particles, we have measured its size, and we have taken next is mass. Because we have done the screen analysis, and on the top screen, on each and every screen, we have to measure its mass. Take out the screen number 4, go to the weighing balance, measure what is the amount of particles, measure its mass, mention the mass here. On the screen number 4, we have 400 grams of mass is there. On screen number 6, we have 300 grams of mass is there. Like similarly, on grams are there on each and every screen. What is my next objective is to find out mass fraction retained on every screen. That means once you know the total mass, right? 100 plus 100 plus 200 plus 300 plus 300. If you summate all the mass, you get a total mass. Now what you do is divide every individual mass by total mass. 400 divided by total, 300 divided by total, 500 divided by total, 200 divided by total. Okay, once you do this ratio, you get this fraction. 400 divided by all the mass, 0.173. 300 divided by all the mass, 0.130. Like that, you calculate mass fraction on each and every screen. Okay, if you summate all the fractions, you get 0.995. It should be close to 1, because when you count all the fraction, it should be equal to 1 from your basics, right? Till here, the mass fraction part is done. Now, cumulative mass fraction. It has got of many uses. That if you go to some shop, you ask for the particles greater than some size. Example, I want 1 kg of particles. 80% of the particles should be greater than 3 mm in nature. Okay, out of this 1 kg, 80%, that means 800 grams of particle should be greater than 3 mm in nature. Once you go, if you ask like this, then you have to do this cumulative analysis. In other cases, in this 1 kg mass, you might have some applications where 80% of the mass should be less than 3 mm. Okay, in this 1 kg, 800 grams of particles should be less than 3 mm. That is what your requirement. Because in some cases you want bigger in nature, in some cases smaller in nature you want. So from this analysis, you can get an idea that what is with you of different size. Example, there are two things. I told you, right? Cumulative mass fraction smaller than dpi. Cumulative mass fraction larger than dpi bar. These are the two cumulatives normally you encounter. How to calculate? When you talk about the cumulative mass fraction smaller than dpi, that means you start counting from the bottom, because smallest thing starts from the bottom. When you talk about the cumulative mass fraction larger than dpi, you should start counting from the top, because bigger particles are from toppers, above screens. Then let us take this example. Cumulative mass fraction smaller than dpi. I have to start from the bottom. Let us start from the bottom. Please catch. Cumulative fraction smaller than 0.073, because our minimum particle, that is diameter, is 0.073. There is no diameter below 0.073. That is why cumulative fraction smaller than this, there is nothing. So that is why it should start with 0. Cumulative fraction smaller than 0.176. What is the fraction? those particle size is smaller than 0.176, only this fraction. That is why this is written. Cumulative fraction smaller than 0.370. That means you have to tell what is the percentage or fraction of the particles is smaller than 0.370 is these two diameters. These two diameters have these two fractions. 0.130 plus 0.130, nothing but 0.260. Okay. Similarly, you have to calculate, right, on each and every screen. For the simplicity, I have given you some numbering here. 1, 2, 3, 4, 5. Number here. This is 1. Some numbering to it so that it is easy for you to sum it. And the final 25. That means what are the fraction of particles which are smaller than 25 mm in nature? That means all these fraction 1 to 7. 0.173 cannot be because 0.173 jo fraction, whatever the fraction it is there, it is greater than or equal to 25. As per the definition, cumulative fraction smaller than 25 mm in nature is up to 7. So that is why 0.822 has come. So what 0.822 signifying is, out of your mass, 82% of the particles are less than 25 mm in nature. Remaining is greater than or equal to 25 mm. Okay, that is how we have to conclude from the cumulative analysis smaller than dpi. Similar way, cumulative fraction larger than dpi. Am I talking about the larger? I have to start from the top. Let us go with the definition. Cumulative fraction larger than 25. Are there any particles larger than 25? Because that screen is of 25 only, right? You don't have the average particle diameter greater than the 25. So what you're supposed to put here? 0. Again, cumulative fraction larger than 0.013. How much fraction is there? This particle fraction 0.173, that is a 0.173. Okay, here 0.173. Cumulative fraction larger than 2.489. These two fractions of particles having larger than 0.249. Okay, 2.489. These two simplicity, again I have given numbering here. This is only 8, this is 8 plus 7, this is 8 plus 7 plus 6. Like that you have to sum it. Okay, let us come back at the bottom. Okay, cumulative fraction larger than 0.073. That means all these will come except this. Okay, that means except the last term, 2, 3, 4, 5, 6, 7, 8, all these things will come. And if you summate all the 7, you get 0.865. Out of your total mass, 86% of the particles are greater than 0.073 mm in nature. So that is what the cumulative fraction larger than dpi signifies. Once you have done with the table, you have to plot two things. Differential plot, cumulative plot. What is a differential plot? If you plot dpi bar and xi, this is a differential plot. Okay. And smaller than dpi, you get blue curve. Okay. The y-axis, you have the fractions, and x-axis you take the diameters. If you plot dpi bar larger than dpi, you get this black line. Okay? That is larger than dpi nature. This is what you are supposed to do in the lab, right? Once you get the mass, you do the screen analysis and weigh them, and finally you make this chart and do the calculations. Finally you have to plot differential and cumulative plot. I hope the things are a bit clear. If you have any doubt, you are free to come and talk to me. Thank you, students. Welcome.